Section 2.2, Power Functions with Modeling. What we're going to cover today are what are power functions, what do we mean by power functions and variations, and specifically we're going to look at monomial functions and their graphs, as well as graphs of power functions that involve fractions as exponents. You're going to find that these look very similar to what we've been talking about with polynomial functions, and in some ways they're even easier than polynomial functions. And it should tie in well with what we already learned in Chapter 1 about the relationships of various functions and how they can be used in geometry and in physics, specifically astronomy with the orbits of planets and some of the other things we've talked about. First, definition, and this should be in your notes. What is a power function? A power function is a function that can be written in the form of f of x equals k times x to the a power. K can be any number you want it to be, any real number, negative, positive, fractions, pi. And a can actually be any real number as well. We are going to be getting into a being fractions and negative numbers. Those were two characteristics that weren't allowed when we were dealing with just polynomial functions. So some examples may help you understand what we mean by k, which is the constant of proportion, or constant of variation, and a, the exponent that we use, the power in the function. For example, the formula A equals pi r squared is a well-known formula. It's the area of a circle. And in this case, we could look at it as just being f of x equals pi r squared. In this case, we would say that the constant, or the power, is 2. And the constant of variation is pi r squared. As you can imagine, it's going to look just like a parabola, something we've already looked at. Simpler version might be the formula for the circumference of a circle. C equals 2 pi r. In this case, the power, while it's not listed, is just 1, because it's r to the first power, and the constant of variation is 2 pi. This would be a line if you were to graph r in relation to c. A more complicated one would be something we're going to be talking about in physics. The force due to gravity can be expressed as k over d squared. And in this case, it's not obvious, but I mean k to be the constant of variation. And our power is actually -2, because notice that d squared is in the denominator, so the power in this case, 2, is actually -2, and that would be the power. When the power is positive, we say that there is a direct variation between f of x and x, and when the power is negative, or if it's in the denominator, we say it's an indirect or inverse variation. So let's look at a couple of these and look at the simpler examples. First, I just want to look at the case where the power is a positive integer. We call those monomial functions. So again, same definition as we talked about in polynomials. N is a positive integer, no fractions, no negative numbers, and I can tell background sounds are going to be very distracting when I record this. So I'll wait. All right, so back to where we were. Let's just look at power functions that are monomial functions. Again, our power is a positive integer, 1, 2, 3, 4, 5, whatever you'd like it to be. But we're not going to be dealing with fractions. We're not going to be dealing with negative integers. And just look at the graphs on these. And these are called monomial functions. An example would be f of x equals 3x squared. Now I've got both f of x equals 3x cubed. Here's the function f of x equals x cubed. We can put a 3 into it as a constant of variation, and we get the cubic graph. You're already familiar with what the parabola or the x squared graph looks like. I want to show you what happens when we take the power up beyond 2 and 3 on the next slide. because we can put in any positive integer as the power right here. N, it can be whatever you want. And here's what some of the graphs look like. I've already graphed them for you. But if you want to take out your graphing calculator and actually try some of these, I think you'll find it a little interesting, more interesting as we get further along. X cubed just starts negative, goes positive. As you probably recall, because it's cubed, it is an odd function, meaning I can take this graph, rotate it upside down, and I still get the same looking graph. It is symmetrical, has rotational symmetry about the origin. X squared is a parabola. It's got reflectional symmetry. It's an even function. The positive x's behave exactly like the negative x's. If we go down, we look at x to the 5th power and x to the 4th power. They look very similar to the other functions we were dealing with. X cubed, x squared, they're almost identical. And as a matter of fact, if you keep taking the power higher and higher, you get a very interesting looking graph to the point where they almost look like straight lines. X to the 100th is even, so it almost looks like two straight lines going up in the air. It's not. There's a little bit of curvature to them, but when you're dealing with numbers very close, you don't have to deal with numbers very much larger than 1 when you take it to the 100th power to get a very large number. So the parabola keeps getting steeper and steeper until it almost looks like two vertical lines. Same with the x cubed function as it goes to x to the 5th down to x to the 99th power. And so that's kind of what monomial functions look like. More interesting case is, what does it look like when the power is a fraction? So again, here's our function, f of x equals some constant of variation, k, so it doesn't really even matter, times x to the a, where a can be any number you want it to be, and in this case, let's just keep it to rational numbers, fractions, be either positive or negative, and I think you'll find this really interesting. In the case of, well, actually, there's several cases we can look at. Here I've got x to the 7/8 power, x to the 4/5, x to the 1/3. Actually, let me do an easier one before we even get started on this. What would it look like if it were x to the half? Well, that's the same as writing the square root of x. Again, we talked about this a couple weeks ago, but x to the 1/2 power is the same as the square root of x. And here comes the bell again. All right, so x is to the 1/2 power, and if you remember, the square root function looks like this. Just goes out to the right. It is not bounded above, although that looks like it's bounded. It does keep rising, so the range of this function goes from 0 to infinity. The domain, x cannot be negative because you can't take the square root of a negative number and get a real number. You end up with an imaginary or complex number. So that's what x to the 1/2 power looks like. Here's some other graphs that I think you'll find are interesting, and we'll look at which ones are even, which ones are odd, and which ones are undefined for x less than 0. In the case of x to the 7/8 power, we get something that almost looks like a straight line, and that sort of makes sense because as 7/8 is very close to 1, and so it behaves very much like x to the 1st power. It almost goes up in a perfectly straight line. Now, it's not quite a straight line, so it gets a little bit of the curve like the square root. Again, it's undefined for x less than 0 because when you take the even power, and you end up not being able to take the 8th root of a negative number. Move over to x to the 4/5. Again, 4/5 is very close to very close to 1. So you get a graph that looks very linear, but you can take the 5th root of a negative number, just like you can take the cube root of a negative number, because a negative times a negative times a negative times a negative times a negative, if I said that the right number of times, is a real number, and a negative number. So it is even because it's to the 4th power. So you notice that when we have an even number in the numerator, x to the 4/5, we get reflectional symmetry about the y-axis. What about the case where we get an odd over an odd? Here's x to the 1/3 power. Again, because we're taking the cube root of a number, x to the 1/3 is like taking the cube root of x, the third root of x. We can do that. It's defined for x being negative. Odd over odd, we get rotational symmetry about the origin. I would actually try to graph several of these on your calculator. You may even want to pause this recording and try that. And try some of these others, x to the 2/5 power, x to the 8/5 power, x to the 6/5 power. See what you get on your graphing calculator before you go on. And here's what we've got. X to the 2/5, even function. And it does look like the square root function just has an even aspect to it because you can take the 5th root of a negative number. X to the 8/5, again, even, but because 8/5 is more than 1, you get something that's a little bit more parabolic in shape. It looks more like the x squared function. And if you think about the fraction 8/5, that's not too far from 10/5, which would be x squared. And so you do get something that looks like a parabola. X to the 6/5, again, it's defined on both sides because you've got the 5th root, and it looks fairly close to a straight line because the fraction 6/5 is fairly close to 1. We can summarize this on the chart that I went through on the previous screen a little bit and take a look at this. Ignore the green line for a second. Focus on the blue and the red. Basically, for positive x's, if your fraction is less than 1, like 1/2, you get a graph that looks very similar to the square root function. On the other hand, if a is greater than 1, you get what is shown in the red line right here, and you get something that looks much more like a parabola, like x squared, or x to the 4th power, or x to the 6th power. When a is 1, you do get a perfect straight line. Now, if it turns out our constant of variation is negative, like k is equal to -2, it flips the entire function or reflects it about the x-axis so that you end up with, just like an upside-down parabola, -x squared, you get the opposite down below. And that sort of makes sense. The question is really, what happens on the left side of the graph when x is less than 0? And I want to summarize that for you right now. All right, one of three things can happen. Either f is undefined, like the square root function, so an example would be x to the 1/2 power, or the square root of x. We don't define it for x being less than 0. It could be an even function, and an example of that would be x squared, the parabola, or it could be an odd function. An example is x cubed. So let me summarize the rules for that and defining whether it's even or odd. First, if it's an even positive integer, then you get a parabola-looking shape and you get an even function, and that makes sense. If it's an odd positive integer, then we get an odd function, meaning it has rotational symmetry about the origin. The more challenging one is here at the bottom when we have a fraction. And we have three cases. Either we're dealing with an odd over an odd integer, odd over even over odd, or odd over even. Now, why can't we have an even over an even fraction? Well, the reason is it can be simplified. If you've got an even number over an even number, like 4/6, you can simplify that fraction so that it is 2/3. So you'll never have the case of even over even. You would just simplify it down. First, let me take this in reverse order. If you have an even denominator, you've got a case where x is undefined when it's negative. You've got a restricted domain like the square root function, x to the 1/2. Because you can't take the square root of a negative number, x can only be positive, and you get a restricted domain. Now, if the denominator is odd, You can take the cube root or the fifth root of a negative number, and so you will not get a restricted domain. You will have a graph on the negative side for x is less than 0. It turns out if it's odd over odd, you have an odd function, and it has rotational symmetry about the origin. If you have an even over an odd, then you have an even function, and it sort of looks like a bird flying through the air, if you will. It reflects perfectly the positive x-axis. Now, again, if these are less than 1, like this case, then you get what looks like the square root graph, where it grows very slowly. If this fraction is greater than 1, you get the parabolic graph, just as we showed on the other slide. So those are the cases. That's basically the lesson for today. And I'm interested in your feedback on whether this is effective or not, and we'll use the rest of the class time to actually work problems the way we would in class.